Welcome to the course Excelling with Mathematical Modeling. Today we will discuss about discrete population models. Let's start with an example. You consider a population of Royal Bengal tigers in Sundarban, which is located in West Bengal. And survey shows that there is a decrease of 3% in the population of these tigers per year. Now, if you want to model this using difference equation, this is how it will go, that your population in the next year will depend in the population of the current year with a 3% decrease. So, 3 by 100 into P. So, very simple model where this gives you number of tigers after n years. This is the number of tigers in the n years. And if you just solve them, it can be just Pn minus 0.03 Pn. So, Pn plus 1 equal to 0.97 Pn. So, if somebody asks that what will be the number of tigers after 4 years. So, after 4 years. For that you need a initial count of the tiger. So, let us say initial count is 150. So, your P1 is 0.97 P0. So, you just multiply and 150 and you get this is approximately equal to 146. Similarly, P2 you put n equal to 0, n equal to 1, 0.97 P1 which is 0.97 into 146 and approximately this is 141. Similarly, you can calculate what is your P3 and your P4. Now, if somebody wants, they can calculate in this manner also, that your P4 which is 0.97 P3, your P3 is 0.97 P2, your P2 is 0.97 P1 and ultimately your P1 is 0.97 P0. So, you have 0.97 to the power 4 into P0. So, this gives you that if you have no information about P1, P2, P3, still you can calculate what is the number of tigers after 4 years just by knowing the initial condition P0. And if you substitute here this 150, this is going to give you 0.88529 multiplied by 150 and this will be approximately equal to 133, which matches with this number. So, a very simple discrete case model using a difference equation where you can calculate the population, in this case it is the Royal Bengal tiger in Sundarban in certain years. Let us take another example. Suppose population, any population, it's a population of persons, grows each year by 2%. But then there is an immigration. this occurs at a constant rate of 3000 per year. So, by immigration we mean that you move out of the one place to another place. So, from that particular place at a constant rate 3000 moves out to some other city, but the population grows at a constant rate of 2%. Now, if you want to model this using difference equation, again Pn plus 1, this population plus there is an increase of 2%, but with a constant immigration of 3000 per year. So, this will give Pn plus 1 equal to 1.02 Pn minus 3000. Now, say population after 10 years we need to know. So, we have already done equation of the form Axn plus 1 equal to Axn plus b. So, this falls exactly in that category, and let us quickly recall this. So, if it is xn plus 1 equal to Axn plus b, so all you have to do is replace this xn by Axn minus 1 plus b plus b. So, it is like xn will be a times xn minus 1 plus b, xn minus 1 will be a xn minus 2 plus b. So, what we are doing is we are substituting this here, simplifying, we substitute xn plus in here and simplifying, and that is how we get the formula. So, here you get a square xn minus 1 plus, I take b common, a plus 1. Similarly, I will write this as x n minus 2 plus b times a plus 1. If I simplify, this is a cube x n minus 2 plus b common s square plus a plus 1. And if we continue in this manner, we will get x n plus 1 is equal to a to the power n plus 1 x 0 plus b times a to the power n plus a to the power n minus 1 plus dot dot plus 1. If you use the GP series formula, this is a to the power n plus 1 x 0 plus b a to the power n plus 1 minus 1 by a minus 1, and in this particular case a is greater than 1. If a is less than 1, this becomes 1 minus a to the power n minus 1 divided by 1 minus a. So, basically we use this formula to solve this particular equation. Let us rewrite this. Pn plus 1 equal to 1.02 times Pn minus 3000, and we have x n plus 1 equal to a to the power n plus 1 x 0 plus some b times a to the power n plus 1 minus 1 by a minus 1. And this is the solution of xn plus 1 equal to a xn plus b. So, if I compare, the value of a is 1.02, value of b is minus 3000, and n we need equal to 9, because I need what is P10, that is the population after 10 years. So, if I substitute this here, I will get P10 is equal to a to the power n plus 1, that is 1.02. So, I substitute n equal to 9 here. So, to the power 10, initial population, let us take 1.5 lakhs plus b, which is minus 3000, then 1.02 to the power 10 minus 1 divided by 1.02 minus 1. If you calculate this, this comes to be 849 minus 32849, and it is 1.5 lakh. So, the conclusion is that okay, you have a growth of 2% in the population with a constant movement of 3000 people moving out of the city. Even after 10 years, the population remains constant to 1.5 lakh. Well, the problem is chosen like that such that you get this answer 1.5 lakhs, but otherwise there will be an increase and the decrease in the population if I change this number 3000. So, let us move to some nonlinear models now. Nonlinear population models. We call them density dependent population growth. As the name suggested, they are density dependent. And the very first in the line is discrete logistic growth. We have done this logistic growth many times. So, I will just discuss the model. The equation is also looking familiar. So, your R is your intrinsic growth rate, K is your carrying capacity, and if you want to find the equilibrium solution, you have to replace xn plus 1, which is xn equal to some x star, substitute the values here and find the equilibrium points. In this case, the equilibrium points will be 0 and k times r minus 1 by r. Since these are populations, they have to be positive, so r has to be greater than 1. And then you can check for stability at these equilibrium points. Since we have done this logistic growth so many times, I am not going in details of this analysis, I leave that to you. Let us move on to another kind of density dependent population growth, and the name is Richer's model. So, this looks like xn plus 1 is equal to alpha times xn e to the power minus beta xn. So, here alpha is your maximum growth rate and beta is the inhibition growth, which means that this is the factor or the parameter which boosts the growth, which increases the growth, and this is the factor with the negative sign which actually keeps the growth down. So, your alpha and beta are positive parameters. Now, if you want to see what are their equilibrium points, so as usual you have to substitute xn plus 1 equal to xn equal to some x star, because there is no change from n to n plus 1, that is the definition of this equilibrium point, and you have x star is equal to alpha times x star e to the power minus beta x star. So, if you solve this, this is alpha e to the power minus beta x star minus 1 into x star equal to 0. So, I have x star equal to 0 and alpha e to the power minus beta x star equal to 1. This gives me alpha equal to e to the power beta x star, which is ln alpha equal to beta x star, which gives me x star equal to ln alpha by beta. So, I have one equilibrium point as 0 and the other equilibrium point as log alpha by beta. Let us now look into the stability analysis. So, our model was in the form xn plus 1 equal to alpha times xn into e to the power minus beta xn. So, let us change this to a function in this form, say fx equal to alpha x e to the power minus beta x, and I have to find the derivative, which is alpha e to the power minus beta x minus alpha beta x e to the power minus beta x. So, it is a product of two functions and you get this. Now, you have the two equilibrium points x star equal to 0 and x star equal to log alpha by beta. So, if you put f mod of f dash x star, the value is 0, you get alpha, just alpha. So, mod of alpha, and that must be less than 1, and this implies minus 1 less than alpha less than 1, but your alpha is always positive, and if I combine these two, you will get 0 less than alpha less than 1. So, this is the condition for stability for the equilibrium point x star equal to 0. Similarly, if I take f dash at the point ln alpha by beta, then I get alpha. If you recall, this is the equation which I get, that is e to the power minus beta x equal to 1 by alpha. So, let me write this one, alpha e to the power minus beta x star equal to 1. So, I am going to substitute x star equal to this value in this equation or some relations in this equation. So, if I want that e to the power minus beta x star, this will imply e to the power minus beta x star equal to 1 by alpha. So, instead of substituting this x star here, I will replace e to the power minus beta x star by 1 by alpha. So, this gives me 1 by alpha minus alpha beta x is ln alpha by beta, this gives me 1 by alpha. So, beta and alpha get cancelled and you get 1 minus ln alpha, and for stability this must be less than 1. So, let us simplify this. I get 1 minus ln alpha is less than 1, which implies minus 1 less than 1 minus ln alpha less than plus 1. Now, let us take this one. If I take this one, it is minus 1 less than 1 minus ln alpha, which gives me ln alpha is less than 2, which gives me alpha less than e square. And if I take this part, 1 minus ln alpha less than 1, I get ln alpha is greater than 0 and alpha is greater than e to the power 0, which is 1. So, combining these two, 1 less than alpha less than e square. So, this is the condition for stability for the equilibrium point x star equal to ln alpha by beta. Now, you can easily check that for 1 less than alpha less than e, you will see that your f dash x star equal to ln alpha by beta, this is positive, and for e less than alpha less than e square, your f dash minus at the point ln alpha by beta is less than 0. So, this means that it is stable in both the cases, but in this case it will monotonically approach the stable point, and in this case it is going to be an oscillatory behavior but approach the equilibrium point. Now, let us look into the numerical solution of this Richer's model. We use the same Microsoft Excel. So, I have taken the value alpha to be 1.535 and this is the beta value. This is already there and your initial value is 50. So, my equation is xn plus 1 equal to alpha times xn e to the power minus beta xn. So, if I want it here, this will be equal to alpha, which is this, multiplied by xn, which is this initial value, multiplied by exponential of minus beta times xn. Now, I will just put dollars in place of the constant. Your alpha is a constant, so I put dollar notation. Then your G4 is xn exponential, again your beta is a constant, so I put a dollar sign and enter. So, I get some values, drag till 50 of them or say 40 of them, just increase the font size. So, let us plot this. If I want to a discrete look, go there, go to this and we choose this scatter and go here. Yes. So, this is what we get for this Richer's model. If I change the value of this alpha, because alpha lies between 1 and e square, if you want a different dynamics, that also can be done. We now look into the solution of this Richer's model by changing the parameter values, namely the value of alpha. So, I have already the equation here and let me now increase this by 1 and drag it to the next 30 values. 3 more. Next, we calculate the initial condition here is 50. So, this is equal to alpha, which is a constant. So, I put a dollar here, multiplied by the xn, which is this value, multiplied minus beta multiplied by x. Since beta is a constant, I put a dollar here and you get the value. So, I drag it till 30 of them. And next we plot it. So, I highlight these values, go to insert, go to this charts and choose this. you want to name the title, so this is just model. If I don't like the grid lines, so I will remove this. If you want access title, so this is your N and this is your X. And you get the figure for the parameter values alpha equal to 6.535 and value of beta remains the same, which is 0.000783, and you see the behavior of the curve is oscillatory and reaching a equilibrium value. The next is we again change this parameter beta value of alpha. We now make it as 15.535 and see what's the dynamics is. So again I increase this value by 1. I take it to the next 30 values and then calculate this xn in a similar manner. So this is equal to alpha, which is a constant, multiplied by xn multiplied by exponential of minus beta, which is again a constant, multiplied by xn, and we get the value. So if I plot this, I again highlight these values. I go to insert, charts, and I get the plot. So in the similar manner, just model, I remove the grid lines, want to put the axis title, so I put it N, and X. So this behavior shows that it is some sort of unstable situation, which we get by replacing the value of alpha 15.535. Now there is a shortcut also. Suppose in this previous figure I want to change the value of alpha directly here. So all I have to do is I have to just replace this value by 15.535. So if I replace this value by 15.535 and just click it outside, you see that all these values are automatically changed and you get the value which is exactly, it's the graph which is exactly same like here. So that is another way of solving with the help of Microsoft Excel. So if we see the result, this is the numerical figures which you will get. So the very first one is for alpha equal to 1.535 and your beta is equal to 0.000783. So, initial value it started from say 50, your x0 is 50, and you reach a steady equilibrium point. Whereas, when your f dash x it is greater than 0, then you get this. However, if it is less than 0, then we get an oscillatory behavior. So, it starts with 50, it jumps up to some level, and then there is an oscillation, a damped one, and slowly reaching the equilibrium point. However, if your alpha does not lie between 1 and e square, if your alpha is greater than e square, you get an unstable equilibrium, and in this case your figure will be like this. So, in this case your alpha is 7.389, sorry, this is 6.535, this is your alpha, and in this case your alpha is equal to 15.535. So, this gives a density dependent population model, namely Richer's model, where you have so many interesting dynamics. So, summing up, today we have learned about these population growth models, both linear and nonlinear, and density dependent models. We have learned about the logistic growth, about the Richer's growth model. We analyzed the model both analytically as well as numerically. We have solved with the help of Microsoft Excel. So, in my next lecture, we will be talking about some banking models which will involve various saving schemes, loan problem, retirement saving problem. Till then, bye bye.